Dear student, warm welcome to NPTEL Phase 2 video course on Geosynthetics Engineering in Theory and Practice. My name is Professor J. N. Mandal, Department of Civil Engineering, Indian Institute of Technology, Bombay, Mumbai, India. The name of the course is Geosynthetics Engineering in Theory and Practice. This lecture number 36. Now this is module 7 and lecture number 36, Geosynthetics for steep slope. The outline of this course is introduction, limit equilibrium design method for circular arc slope analysis, general guidelines for the design of reinforced soil slope, Kimmersmann's simple sliding wedge method, Lavan's method for slope stability, Joel's method for slope stability analysis, back wrapping technique for reinforced soil slope, geosynthetics for in situ slope stabilization, textile technique, and design of a 300-meter high artificial mountain using geosynthetics. So regarding this steep slope stability, the use of the geosynthetics material to reinforce the steep slope or the embankment are very common. In general, if the slope angle is less than 70 degree, we can consider it is as a steep slope. And we will use the limit equilibrium method via a circular arc failure plane, and this kind of the steep stability problem also can be applied for the reconstruction of the failure slope, which can aid in compaction at the face of the slope. Also there is a possibility to reduce the surface erosion. Nowadays, a lot of NHI projects are going on where it is required to reconstruct a major highway. Also gaining of additional slope at both at the toe as well as top of the slope, where you require what will be the length of the reinforcement, what will be the spacing between the two geogrid layers. So detailed slope stability method are nicely adopted by various computer modeling, and I will show you some of the design chart where the number of the excellent design chart also are available, in which we can use and we can solve the various problems related with the slope stability. Now, as you know, slope may be man-made or the natural, it may be unstable and failure may occur. In such a case, the conventional method will be very expensive, and sometimes it is very difficult to construct as per the desire of the owner. Introduction of geosynthetics as primarily and or secondary reinforcement will enable to construct a stable slope over foundation soil. The primary geosynthetics reinforcement is placed horizontally to stabilize the steep slope against the potential global failure. Sometimes it is required to stabilize the face of the slope by providing relatively small and closely spaced secondary reinforcement. I will show you later what is the secondary reinforcement, how you can place the secondary reinforcement in a slope, and why it is required to introduce the secondary reinforcement along with the primary reinforcement along the facing of the slope. So, this is a short edge strip, or by wrapping the geosynthetic reinforcement at the face during the fill placement and the compaction. So, this it is needed to protect the slope from the erosion. In such case, geo meshes or the geocell fill with the soil can be also used for vegetation. The most important is to provide the chimney drain and the geotextile wrap drainage pipe behind the reinforced soil zone to eliminate the seepage forces. It is also very important, as in the case of the reinforced soil retaining wall, you have to provide with the drainage at the back of the geogrid reinforced soil retaining wall. Similarly, for in the case of the reinforced soil slope, you should also provide proper kind of the drainage behind the reinforced soil zone, and that will eliminate the seepage forces. Christopher et al. 1990 reported that if the face inclination is less than 70 degree, it can be considered as reinforced soil slope. If the face inclination lies between the 70 to 90 degree, it can be considered as reinforced soil wall. Various design, guideline, specification and the manual have been provided by Christopher et al. 1990, Berg 1993, as well as by Elias and Christopher 1997. So, various synthetic reinforced soil specification and design also are available. So, we are to know that how to design the reinforced soil steep slope, and also you have to remember it should be the less than 70 degree, it may be 60 degree, it may be 50, 40. So, then you can consider it is as a reinforced soil slope, and if it is more than 70 degree, 80, 90 degree, then you can design on the base of the vertical reinforced soil retaining wall, which we have already covered earlier. Also, we have to be careful at the facing of the slope, and facing of the slope sometimes require for the secondary reinforcement, that also will help you for the proper compaction near to the slope of the face, as well as it will also eliminate the surface erosion. And sometimes also along the slope you can provide with the geocell material, which can provide, grass can also grow, and also it will stable, and you can have a very greenery slope. There are also the other kind of the system where you can use that fiber with the soil, and also the grass can grow. So, this kind of the system also have been applied. So, now here you can see different types of the arrangement of the reinforcement. So, arrangement and placing of the reinforcement has a very important role. You can see here that equal length reinforcement with equal spacing. Spacing is the same, but it is the equal length. So, you have to optimize the design. Sometimes it is required to optimize the design. You can see that you can make a spacing is equal, but different in length, that bottom is minimum and top is maximum. On the other hand, you can see here in the spacing is equal, but difference in length, that bottom is maximum and top is minimum. So, you have to optimize, you have to check which one will be the much more stable reinforced soil slope. You can see equal spacing with one layer secondary reinforcement. this is the larger one is the primary reinforcement. This is primary reinforcement. You can see in between that one small length of the reinforcement or the short length of the reinforcement, which you call the secondary reinforcement. But spacing is the same, but you can provide some secondary reinforcement. So it is equal spacing one layer with the secondary reinforcement, or equal spacing with two layers of the secondary reinforcement. Sometimes I can say that if the spacing between the two primary reinforcement is 1 meter or more than 1 meter, then it is necessary to provide with the secondary reinforcement. So sometimes it is that one layer of the reinforcement as a secondary reinforcement, and sometimes it is required two layers of secondary reinforcement. So principal application of reinforced soil slope are reported by Tension 1987. When new slope construction, widening of the highway, alternative to retaining wall, repair or fail landslide slope. Nowadays, infrastructure, transportation, residential, commercial and industrialization are developing rapidly, causing the requirement of land availability. I will show you some of the figure where you can see that how you can make use of the land and how you can save the land. In first case that it is an uninput soil, and what this is the vehicle can pass through this. This is a certain slope, 2 horizontal to 1 vertical. So maximum land required for the slope stability when you want to construct a uninput slope. On the other hand, you can deploy the geosynthetic material which can save this land. So you can provide with this number of the layer of the geogrid material and construct a very steeper slope. So this is the unreinforced stable slope, but you don't require this unreinforced case. You can provide with the steep reinforced soil slope. So this reduced fill is requirement. So you can use this new places. These are the new places where you can use. So you are saving a land. So by the introduction of the geosynthetic material, so we can see here that how you can save the land, and you know that land is very expensive. So with respect to the conventional method, if you can adopt the alternative geogrid reinforced soil slopes, steep slope, then you can see how we can save the land. Also, you can widening of the road by making the existing slope much more steeper. For example, that this is the here widening of the road by making the existing slope steeper with the inclusion of the reinforcement. So you require the steeper slope. It is for example, this is the existing road over here where the vehicle is passing here, and you want to do widening of the road. In our lot of NHI project where it is required for the widening of the road. So if it is a widening of the road, you can see that you can introduce this number of layer of the geogrid reinforcement. You can make a slope of 1.5 horizontal to 1 on the vertical, and you can increase the land. So vehicle can pass through this. So it is also sometimes required that widening of the road by the existing slope steeper with the inclusion of the reinforcement material. So when it is required to increase the land, yes, you can use the steeper slope, and when it is required that you want to save the land, yes, you can do that by introducing the geogrid reinforced steep slope. Now, instead of conventional retaining wall, geogrid reinforced soil wall can be constructed. So, for example, this is the road and you are using the conventional retaining wall here, conventional retaining wall, which will be the very expensive. So, instead of that, you can use the geogrid reinforced slope when it is required, you can use. So, it will be much more economical. Also, repairing of the failed of any landslide slope can be possible with the inclusion of the geogrid reinforcement, and most of the landslide you can say because proper not design and proper no drainage kind of the system has been applied. So, you can use this geogrid material to protect the landslide slope by the introduction of the geosynthetic material. Some type of typical reinforced soil slope section is shown here. This is the cross section of the reinforced slope structure, and this is the geosynthetic reinforced soil slope over the firm foundation with the drainage. I am showing you here. So, this is a stable foundation of the soil or farm or the foundation is a bedrock, and this is the slope, steep slope, and this is the number of the layer of the reinforcement, and this larger length of the reinforcement is considered as a primary reinforcement, and this smaller or short length of the reinforcement we consider as a secondary reinforcement. And at the back of this slope it should provide with a proper kind of the drainage system. So, here it is the chimney dam, and then you can provide with the geotextile wrap drainage pipe. Here it is geotextile wrap drainage pipe. So, this geosynthetic reinforced slope over the firm foundation with the drainage. So, drainage is very important. So, most of the time if you do not provide the drainage, and there is a possibility for the failure of the structure. So, you should provide the drainage, and similarly also the reinforced soil slope also for different purpose also you can use. So, for a example that you can want to construct a house near to the slope, and at the bottom of the slope where the vehicle are passing, and then the house may collapse. So, you can provide with this kind of the system. You can see here that you can make a steep reinforced slope, and also you can construct a house here. Also in the front, some places also in the hilly area where there is a building, and this portion almost is going to be a collapse. So, he is provided with a wrap around geotextile reinforced soil slope. So, that way you can protect the house in the sloping step. So, failure mode of the reinforced soil slope after Berg et al. 1989, and there is a possibility for internal failure, external failure, and compound failure. So, this is the internal failure, that means failure surface passes through the reinforced zone. This is the external failure, that failure surface passes behind and underneath the reinforced soil zone. And compound failure, the failure surface passes behind and through the reinforced soil zone. So, there are different types of the failure. It may be the internal failure, external failure, and compound failure. So, we have to check that in terms of the factor of safety. Now, what theory we will adopt for different types of the soil? So, initially I will now discuss about the conventional method and what will be the limit equilibrium method for the design of the slope. So, if we will will use the circular arc slope analysis considering the cohesive soil when pi is equal to the 0. So, it is a limit equilibrium design method. So, for the example that this is the stability analysis of a slope in a homogeneous clay soil where pi is equal to the 0, and this is the foundation and this is the embankment. The embankment, this is the slope, this is the slope here, and this embankment has its own weight which we designated as W of E, that means weight of the embankment. Similarly, this part is the foundation. So, this foundation also has its weight which we call the weight of the foundation, which is designated as W of F. So, this W of E here, this W of E is the weight of the failure zone at the right side of the center of the circle. This is the failure zone and this is the origin, and which is making at an angle of theta, and this is the radius is r. And this x1 distance between the right side weight and the central line, this is the x1, and this is the Wf is the weight of the failure zone at the left side of the central line, and this is the x2 is the distance between the left side weight and the central line, and r, as I said, it is the radius of the failure circle, and theta here is the angle by the failure arc at the center of the circle, and this is the C, this is C. So, C is mobilized cohesion along the failure surface, and the tower is equal to shear strength of the soil, which we call the C of U. Cu is the undrained cohesion of the soil, and you have to check what will be the factor of safety against the slope failure. So, we have to check what will be the factor of safety against the slope failure when pi is equal to the 0. So, we have to calculate what will be the driving moment and what should be the resisting moment. So, driving moment, that means this is the weight W of E, weight of the this part embankment. So, WE, it take a moment, this is the O. So, then WE into x1 minus this is the weight of the foundation here. So, WF into x2, because it is lying on the left hand side for the central line. So, we can write that driving moment will be equal to WE into x1 minus WF into x2. And what is the resisting moment? This is the resisting moment along this arc. So, this is the C is the cohesion which is acting along this surface. So, R is the radius, theta is the angle, so C into this arch, that means A, E and D. So, this resisting moment will be equal to C into R theta into R, that means C into R square into theta. So, resisting moment C R square into theta. So, for the equilibrium, then this resisting moment will be equal to the driving moment. So, here it is shown that resisting moment is equal to the driving moment. So, this is the driving moment W into x1 minus Wf into x2 is equal to C R square into theta. So, from this you can calculate the C. So, C will be equal to W into x1 minus Wf into x2 divided by R square theta. Now, you have to calculate what will be the factor of safety against this sliding. So, factor of safety will be tau f by C. So, tau f means C of U, because this is tau f is equal to C of u. So, Cu divided by C. Now, this Cu by C, that means that if the circular surface is the one for which the ratio, that means Cu by C is a minimum when the C is the maximum. So, you have to find out what should be the circular surface for the sliding. So, a number of the tall arc are to be made for the different tall circle. You have to go for the different tall circles. So, minimum value of factor of safety you can obtain, and that minimum factor of safety will give you what will be the factor of safety against the sliding for the slope, and the corresponding circle is the critical circle. So, you have to check. So, this is the case of the unreinforced soil slope and how you can calculate the factor of safety. So, you can calculate the what will be the driving moment, also you can calculate what will be the resisting moment, and you can take the ratio and check up that what will be the factor of safety against this sliding. So, now if it is a reinforced soil slope, so what will happen? So, in case of the reinforced soil slope, we are considering for cohesive soil and shear stress does not rely on the normal force on the shear plane. So, no slices are considered in the analysis. So, initially we are showing on a single layer of the reinforcement. So, we know that in case of the unreinforced soil, what is the factor of safety against sliding? That means you know that C into L into R, that divided by W into X plus QD. Let us consider that if we consider the one layer of the reinforcement here. This is the reinforced soil slope. We are providing, let us say, one layer of the reinforcement. Okay? And this is the slope, and there is also some load which is designated at Q, and the height of the slope is H, and this is the shear circle, and this is the center of the circle is O, and this arc length is L, this arc length is L, and let us say there is no reinforcement in the beginning. So, this embankment has a weight, let us say this is the weight W, and which is located at the from the center of the circle at a distance of x. So, when there will be no reinforcement, you have to check what will be the factor of safety for unreinforced soil. So, factor of safety for unreinforced soil, if I say F of SU, this will be equal to, this is the C and this arc length is L, this is L, this is L. So, that means C into L into R, that means C into L into R. This is the what we call the resisting moment divided by driving moment. Driving moment is due to the weight of the embankment. So, W into X, so this is W into X plus due to this surcharge load Q, that means Q which is located at a distance D from the center of the circle. So, Q into D. So, this will be Q into D. So, first of all you have to calculate what is the factor of safety for unreinforced case. So, you know the C, you know the L, you know the R, you know W, and what it is located, you know the surcharge load. So, you can calculate what will be the factor of safety for unreinforced case. Now, if you introduce, for example, in case of the unreinforced soil, if it fell, if this factor of safety is less than 1, then it is required for the deployment of geogrid material along the slope. Now, if we introduce this one layer of the reinforcement here, okay, which will give some horizontal forces, that is T of horizontal. Now, in the reinforced case, so let us say that factor of safety for reinforced. So, there is a resisting moment and also the driving moment. So, this resisting moment, one is MR in no unreinforced case, plus this resisting moment due to the introduction of the geosynthetic material. Let us say this resisting moment is increasing, and that resisting moment, let us say delta of M of R, this divided by driving moment is equal to M of D. So, this factor of safety will be equal to M of R plus, for this increment is due to the introduction of geosynthetic material. Now, this resisting moment will be equal to, this is the T horizontal, which is the geogrid tensile strength, this into this distance, if we take moment in the origin. So, T horizontal into Y. So, this delta MR mean T horizontal into Y, this divided by MD. So, we see that this part is increment. That means delta of MR is T horizontal into Y, and that is the reason there is a increasing the factor of safety due to introduction of the geogrid material, because this part will be on the higher value and this is constant. So, this factor of safety will be on the higher side. If in the unreinforced case, if the factor of safety value is less than 1, then you can introduce the geogrid material. So, you can introduce the even then number of geogrid material. If you place at the one layer of the geogrid material in between the foundation and embankment, if it does not satisfy, you can give 2 layer, 3 layer, 4 layer, and see that what it will satisfy this factor of safety. Even then, sometimes if it is required for the construction of the embankment, very high strength of the geogrid, which also can help you to stabilize the structure. So, here also I just mention here that C is the undrained coefficient. Sometimes this C undrained coefficient you can take 0.5 times of Q of U, where Q U is equal to unconfined compression strength of the soil. And also when you are introducing the geogrid material, this part is the L of E, what you call the required that embedment length of the geosynthetic layer. So, what should be the length of the geogrid behind this failure surface, that also is important to ask. And here you can see that when you are introducing the geosynthetic material, there will be a allowable tensile strength of the geosynthetic layer in this direction, and also there will be a inclined, that means tangent component of the allowable tensile strength, that is T of incline. Here is also the question that sometimes the geotextile material may be failure line, it may not be like this. So, it may be tangent to the failure surface T inclined, or it may be in between this angle. It may be that T inclined and also this any angle you can optimize and also can be calculated. but in the horizontal it can give the more value, but T inclined he may give the less value. Also you have to optimize, and also you can find out what will be the tensile strength of the geogrid material is required for the stable slope. So this also is to be taken care for design. Now as I said that we can do the number of the layer of the reinforcement. Now you can see here that this is the slope, the height of the slope h, this is the radius, and this is the center of the circle, and this is O, which is x and y, and you provide the number of the layer of the reinforcement. So for example, that you can see here, this is one layer of the reinforcement whose strength is T1, another layer of the reinforcement with tensile strength is T2, like that in number of reinforcement with tensile strength is Tn. So we are introducing number of the layer of the reinforcement, and this reinforcement is located at a distance of y1 from the center of the circle. This T2 is located at a distance y2 from the center of the circle. This Tn also located yn distance from the center of the circle, and this is the weight of the embankment which is located at a distance of x, and this is the toe of the slope, this is 0 0, and this I say the cohesion, that is C, and this article length is which you call the L, and this is the height of the wall. So what we are to calculate that what will be the minimum factor of safety can be obtained by varying the radius and the coordinate of the center of the circle. So it is very difficult sometimes to solve the manually. So that's why there are many ready-made computer program also is available. So you can make use of that for the reinforced soil slope. So we know that what will be the factor of safety for the reinforced case, multi-layer reinforced case. For example, the factor of safety we calculated the resisting moment divided by this is delta mr divided by driving moment. Now this delta mr is due to introduction of the reinforcement. Now if you use the number of the layer of the reinforcement, that means this delta of mr will be equal to summation of 1 to n, that means Ti into Yi. So you can take this value T1 into Y1 plus T2 into Y2 plus like that Tt into Y2. You can give the spacing, also you can vary 0.5 or 0.1 meter and check that when the factor of safety in the reinforced case will be the stable, or this value will be equal to greater than 1.3 or 1.5 for slope stability problem. So you can do the number of the reinforcement layer. For this unreinforced soil slope with the limit equilibrium condition. So here you can see this is the soil where C is equal to the 0, and this is the pi soil. This is the embankment, and this is the foundation, and this is the center of the circle whose coordinate is x and y, and r is the radius of the circle. This is the toe, and this is the crest. So first of all we are considering it is a unreinforced soil slope in limiting equilibrium condition. We take that strip, and this is the W weight of the slice. We take one slice here. So this is the weight of the slice W, and pi is equal to angle of shearing resistance of the soil, and this is the alpha. You can see tangent to this horizontal, which is alpha. This is the slope of the tangent to the circle of the slide at the strip circle, and r is the radius. So we know that how to calculate the factor of safety with this equation. It is also known to you, you know that Bishop method. So, this is W into tan of pi into sec alpha into R divided by 1 plus tan pi into tan alpha divided by factor of safety, this divided by summation of W into sin alpha into R. So, this is what factor of safety is required. So, you assume some factor of safety and you know all this value, you know the what will be the weight, and you know the what will be the alpha value, you know the R value. So, you substitute this value and check that what will be the factor of safety required and what will be the factor of safety you assume. So, this is by like a trial and error and check up that what will be the factor of safety in case of the unreinforced soil slope. So, this is for C is equal to 0 and pi soil. Now, in case of the reinforced soil slope, single layer reinforcement, only single layer reinforcement which has been placed at the embankment and the foundation soil. This is a single layer reinforcement whose tensile strength is equal to Tg, and this is the center of the circle xy which is making at an angle to the vertical theta, and this is the toe 0 0 and this is the crest, and this is the R is the radius of the circle, and this is the failure surface. Only here we introduce one layer of the reinforcement which tensile strength is Tg. Here weight of the slide Wg and alpha, you know what we are making at an to the horizontal to the tangent is theta. So, you can calculate that what will be the additional resisting moment due to the introduction of this reinforcement, that is Tg into R cos theta. So, this theta angle by the circle radius with the central line at the intersection of the slip circle and the reinforcement. So, this additional resisting moment that due to the reinforcement, if it is a delta Mr, will be equal to this is Tg into R into cos theta. Now, you can see this is the equation which I have shown you earlier, that factor of safety for unreinforced case, but due to the introduction of the reinforcement, this required factor of safety will be equal to, this is for unreinforced case, plus if you add this, that is delta Mr additional resisting force, that is Tg into R cos theta, R is cancelled. So, this is Tg cos theta. So, this is the additional part due to the introduction of the reinforcement. So, here again you can calculate what will be the factor of safety, and this factor of safety required is 1.5 in generally. So, from this equation also you can write the equation like this, that is Tg is equal to Fr summation W sin alpha into summation of W tan pi sec alpha 1 plus tan pi by tan alpha divided by Fr into sec theta. So, you can directly determine what will be the tensile strength of the geogrid material. Once if you assume some value of factor of safety and you find out what will be the required factor of safety. When you know that required factor of safety is 1.5 generally, then it is okay. So, with the introduction of the geosynthetic material, if you find that Fr factor of safety is 1.5, then it is okay. So, if you know that what will be the factor of safety, suppose 1.5, then you can calculate what will be the tensile strength of the geogrid material. So, you can calculate. So, if the unreinforced case, if the factor of safety is less than 1, then only you can introduce the geosynthetic material as a reinforcement for stability analysis. Now, we will discuss the circular slope analysis considering C pi soil. Now, we consider C soil, we consider pi soil. Now, if it is a C pi soil. So, in case of the C pi soil, we will consider slip circle analysis using the modified Bishop method. So, we will consider that modified Bishop method. So, you have to take this is you can see in this slope and this is the B of I. That means this is width of the slice I. Bi is the width of the slice and it has also has a weight. That means weight of the slice, it also has a weight and the weight of the slide let us say W of I. We are considering the CPI soil and this is the lever arm for this slice I and this L and the center of the rotation XC and YC, XC and the YC and that is the coordinate and this is the lever arm for the geogrid I for this section and this is the alpha of I which is inclination of the base from the horizontal for slice I and this is the resisting force of the geogrid. This is T of I and you know R is the radius of the potential failure surface and let us consider that N is equal to total number of the slice considered. N is equal to total number of the slice considered. Let us say here that what I say that F factor of safety, C bar is the effective cohesion of the soil at the base of the slide, Bi is the width of the slide I, Wi is the weight of the slide I and there is a development of the pore water. So, this is also important. Ui is equal to pore water pressure on the base of the slice I, pi dash is equal to effective angle of friction at the base of the slide, alpha 1 inclination of the base from the horizontal for slice I and Ti mobilized tensile strength of the geogrid and Yc is the y coordinate of the center of the slip surface and Yi is the y coordinate of the geogrid I. R radius of the potential failure surface, N total number of the slide considered and I is equal to slice number. So, from this you know that Bishop method, this is the equation F is equal to summation of I is equal to 1 to N C dash into Bi, this is the C dash and this is the B of I plus this is Wi minus Ui into Bi because they to put pressure into tan of pi dash into sec alpha I, this divided by 1 plus tan pi dash into tan alpha I divided by F plus summation of I into 1 Ti Yc minus Yi divided by R, this whole divided by summation of I is equal to 1 to N Wi into sine of alpha I. So, this is the modified Bishop method for the CPI soil. So, here both the CPI soil has been considered and pore water pressure also has been considered. So, this is the equation. So, this you know the equation for the circular slope analysis for the CPI soil. Now, in the analysis the interslide forces are neglected. The factor of safety should be within 1.25 to 1.5. For stability equation can be written as MD should be less than equal to MRS plus MRR, where MD is equal to disturbing moment due to the weight of the failure zone plus the surcharge, MRS is resisting moment due to the strength of the soil and MRR is the resisting moment due to the reinforcement. So, it should be that MD should be less than equal to MRS plus MRR. Now, you have to calculate also the embedment or what we call the anchor length LE. That means what will be the length of the reinforcement behind the failure surface LE. So, LE can be determined using this equation. LE is equal to P into Fs divided by 2 Ci into sigma n tan pi I, where P is equal to pull out resistance, Ci is equal to interaction coefficient for pull out, which is dimensionless, sigma n is equal to normal state on the geogrid reinforcement, pi I is equal to peak angle of friction for reinforced soil, and Fs is factor of safety against the pull out failure. So, minimum required anchor length behind the potential shift circle should be 1 meter. If it is less than 1 meter, then at least you should consider that is 1 meter. Now, construction of the reinforced soil slope. So, first of all, you have to prepare the site. You remove all the grass and the debris and prepare a uniform subgrade using the roller or rubber tar vehicle. Now, how to construct the face construction? If the slope angle beta is greater than the angle of the friction pi of the soil, a wrap face is to be provided to prevent the erosion or the sloughing. So, what is required? You have to provide a like this, you have to provide a form work, this is the form work. Okay. So, initially you have to be clean and use the light oil compaction equipment at the base and use the ordinary compaction, and then this is the primary geosynthetic material. So, this is a wrapping around you are doing, but you have to provide a form work is to be placed to support the steep slope face during the construction. And then this lip thickness generally considered about 500 millimeter to 600 millimeter. So, one has to maintain that spacing between the two reinforcement. And this face wrap for the angle which should be the greater than 40 degree to 50 degree. Then again you can remove the formwork, then you can place here the formwork, and then the geogrid also, it is in the roll wrap form. So, it can be open and can be placed like this. So, you can construct this wall like this. So, this is construction step, as I say, A, that is the lift 1 plus reinforcement to lift 2, then lift 2 with the face is wrap, and then the C lift 2 and then it is completed. Like that you can construct the reinforced soil steep slope. So, it can be prevent for any sloughing. There is a possibility for the sloughing to the side slope. So, that is why it is needed to provide a kind of the form work. Then placement of the geosynthetics. Higher strength is required along the width of the slope. Therefore, it is recommended to place the geosynthetics with machine direction along the width of the slope. It should not be wrinkled. To protect from the wind, the geosynthetics should be anchored with the aid of the sandbag or pins. A minimum overlap length of 150 millimeter should be provided while stitching the two geotextile material. Placement of the backfill and compaction. Place the backfill material over the geotextile and compact it with a rubber tar vehicle for cohesive soil or using roller for granular soil. A minimum 150 millimeter thickness should be maintained between the wheel of the roller and the geotextile reinforcement. Always lightweight compaction should be used near the face of the slope. So, it should maintain. The compaction should be achieved about 95% of the standard maximum dye density within plus minus 2% of optimum moisture content. Then repeat the procedure with the next layer of geotextile and backfill and so on. And vegetation are to be provided at the face of the slope to prevent the soil erosion. So, you can have some idea about that how you can place this geotextile material and how you can construct the slope using the flexible material, how you could wrap, how you should compact, what density you should achieve. In order that there should not be any sloughing of the slope or there should not be any the erosion at the face of the slope. And in addition that there you should maintain the minimum spacing between the two reinforcing material during the compaction, otherwise that there is a possibility for the damage of the geosynthetic material. With this I finish my lecture today. Let us hear from you any question. Thank you for listening.